Even though the Bayesian information criteria contains the word Bayesian in it, it's not really a fully Bayesian procedure. And it's most helpful in the context of problems in which you can compute or you obtain the maximum likelihood estimators of the parameters as part of your inference. Now, when you're using the MCMC algorithm to fill a fully Bayesian model, computing the MLEs is not straightforward just from the output of that algorithm. And therefore, we would like to use a different mechanism to provide full inference. And in particular, we would like to obtain a mechanism to find the full posterior distribution for the number of components. We would just like to treat it as another parameter in our model. So that's what I want to discuss today. I want to discuss fully Bayesian inference for capital K, the number of components in the model. And what we're going to do for inference on the number of components in the model is we're going to try to draw a difference between what we're calling capital K, which is the maximum number of components in the mixture, and something that I'm going to call K star, that is the number of components that actually generated observations. So this distinction is important because the Bayesian approach to selecting the number of components that are present in the sample, which essentially boils down to this K star, is to say I'm going to allow a very large number of components in the mixture in principle, thinking that not all of those components will be occupied by observations or would have generated observations. And I'm going to let the data tell me how to shrink from that maximum number of components, capital K, to a smaller number, K star, that is the one that is actually being used in the data set. So the implicit assumption is that K star is less, and often much less than capital K, the largest number. Now, to do this successfully, we need to be a little bit careful about how we elicit the prior distribution for the data. Remember that so far, we have been using a prior for omega that is a Dirichlet. And in particular, we've been using a very particular type of Dirichlet that is a Dirichlet 1, 1, 1, that just boils down to a uniform distribution on the simplex. Now, this prior has been helpful while we keep capital K fixed, and we have a good idea about what K star is, and in particular, we think that K star and K are about the same value. But if we're going to move now into this other setting where we're going to say that K star is a much smaller number than capital K, then using a prior of this type won't work, because basically what will happen is that as we increase K, we're also increasing what our prior guess is about capital K star. So in other words, our prior will be, if we use this prior, the maximum number that we select as capital K will have a lot of influence in the posterior inference that we get out of our model. So instead, I want to work with a different version of the Dirichlet prior. And it's one that will allow us to keep the behavior of the prior in some sense stable as capital K increases. And that prior is a prior of the form 1 over capital K, 1 over capital K. Or more generally, I don't have to do ones. I can use some other constant value. And we'll discuss in a minute how to select those constant values. Call it alpha and alpha. So a prior of this type, the advantage that it has is that as I grow this capital K, that is just going to be, in some sense, a tuning parameter in my model, in my algorithm. As capital K grows, what I'm saying is that every individual component has a priori a smaller and smaller and smaller probability. And what that does is that a priori, the value of capital K is going to be bounded by a certain quantity.
So if omega 1 to omega capital K is given a Dirichlet prior with parameters alpha over K, alpha over K, all the way for all K values that I need up there. Then there is a little mathematical result that tells us that if I want to compute the limit when capital K goes to infinity, remember that this is the maximum number of components that I allowed, of the expected value of K star, that is among the maximum components that I'm allowing, among the capital K components, how many of them are actually occupied by data or were generated data in my sample. So which ones are filled, if you will. So that this quantity is equal in the limit to the sum from I equals 1 to n of alpha divided by alpha plus I minus 1. And in turn, this quantity can be roughly approximated by alpha log of n plus alpha minus 1 divided by alpha.
So the first part of the result is a little bit outside the scope of this class, so I won't be working out a proof for this. But the second piece is actually relatively straightforward. So this approximation using the alpha log n plus alpha minus 1 divided by alpha. And that approximation just comes from basically thinking about the sum as an approximation, a Riemann sum approximation of an integral. So one way to think about it is to say that, this quantity just comes from doing the integral between 1 and n of essentially a function. Now I'm going to replace I that is kind of discrete with a continuous index. So I'm just going to say alpha divided by alpha plus x minus 1 dx. And we can easily solve this integral, and the solution to this integral is just this expression here that involves the logarithm. So that is kind of what justifies this approximation. As I said, the first result I'm really not going to justify in detail. But now that we know that the expected value of K star is at least approximately equal to alpha log n plus alpha minus 1 divided by alpha, we have a way to elicit the value of alpha that we want to use for our model if we have a way to elicit an expected value for the number of occupied components. So given so we need a rough guess of what the expectation of K star is. If you remember, for example, in the GALA-6 data set that we have been discussing across the class, we had a good reason to think that K star was around 6 because the data was collected from 6 different conic sections of the sky. So that means that making a guess that K star is around 6 makes sense. And once you know what the guess is for this expected value, then you have a nonlinear equation, but that you cannot easily solve by hand, but you can easily solve it in the computer, and we'll see an example later on. And once you solve that equation, so given this value, you solve for alpha in that equation because you also know the number of observations that you have. And so that gives you a mechanism to elicit the prior that you're going to use, or the value of alpha that you're going to use to define your prior for the omegas.